Dear students, welcome to the fifth session of our Chapter 3 Classification of Elements and the Periodicity in their Properties. Today we will discuss about the periodic trends in the chemical properties. And there are three periodic trends. The first one is periodicity of valence or the oxidation states. Second one, anomalous properties of the second period of elements. And the third one is the chemical reactivity. Let's talk about the first one, that is periodicity of valence or the oxidation state. The valence of representative elements. What do you mean by representative elements? It constitutes the group 1, group 2, group 13 to 18. All the elements represent representative elements. So what it is equal to the number of electrons in the outermost orbital. The valence is equal to the number of electrons in the outermost orbital, or we can define it is having or it is equal to the 8 minus the number of outermost electrons. We can get the valence of each period. But some periodic trends we can see in the valence of elements like hydrides case and oxides, and that we will discuss in the table. That is, if we are having a group 1, what is the number of valence electron? 1. So its valence is 1. 2, 2 itself, 3, 3 itself, 4, 4 itself. But after 4, what happens is the number of valence electron here comes 5, 6, 7. But what about the valency? It becomes either 3 or 5. That is 8 minus 5 becomes 3. And the possibility is either you can lose the 5 electron. So this is the number of valence. 16th group, when it comes, the number of electron is in the outermost shell is 6. So what we can do is 8 minus 6 is 2 valence. Or you can remove all 6 electrons from the outermost shell. The same way we can say for the valence 17th group, 8 minus 7, 1 or 7 electrons to be removed. So it becomes the valency of these groups. Similarly, 18th group, if we are having 8 electrons are there in the valence electron or in the outermost shell. So what about the valency? 8 minus 8 is 0. Or we can remove all the 8 electrons. So the possibility of the valence is what? 0 or 8. So like this we can say the periodicity of oxidation state in the periodic table. The oxidation state of an element in a particular compound can be defined as the charge acquired by its atom on the basis of electronegative consideration from other atoms in the molecule. And each group has a common positive or negative oxidation state, and it shows gradual change in the oxidation state in a period. Now let's see this question, that is, using the periodic table, how we can predict the formula for the compounds by the following pairs, that is silicon and bromine, aluminium and sulfur. For that what we have to do is we have to take the group, which group the element belongs, and also its valence. If we know these two things, we can make the formula of the compound. First one is silicon and bromine. We know that silicon belongs to group 14 and its valence is 4. On the other hand, bromine belongs to the halogen family, that is group 17, and its valence is 1. So using the valency method, how we are doing? We will write the symbol of the elements, silicon Si, bromine Br. Below that we will write the valence, silicon plus 4 and bromine minus 1. Doing the crisscross, we will get the formula as Si minus 1 Br plus 4. Remove the minus and plus, then we will get the formula as SiBr4. This is the formula of the compound. Same way the second one, aluminium and sulfur. How we will do? Aluminium belongs to which group? 13, and its valence is 3. On the other hand, sulfur belongs to 16th group and its valence is 2. So we will write Al and S. Below that the valency will be plus 3 and minus 2. Doing the crisscross, we'll get Al minus 2 S plus 3. Remove the plus and minus, we'll get the formula as Al2 S3. Like this, whatever the compounds are there, We can write the formula if we know the element symbol, its group number, its valence. We can use the valency method and get the formula. So this is how we are writing the formula of the compound. The anomalous properties of the second period elements. The first element of each of the groups, that is first group lithium, second group beryllium, and group 13 to 17, it consists of boron, carbon, nitrogen, oxygen, fluorine. It differs in many respects from the other elements of their respective group, and it is due to the small size, large charge to radius ratio, and also the high electronegativity. So these are the three reasons with which we are having some anomalous properties for the second period elements. In addition to this, the first member of the group, they have only 4 valence orbitals, that is 2s and 2p orbitals available for the bonding, whereas the second member of the group, they have 9 valence orbitals, that is 3s, 3p and 3d. Because of this reason only, they have some anomalous properties. See this periodic table where we have taken the second period, lithium, beryllium, boron, carbon, nitrogen, oxygen and fluorine, they will be having only the 2s orbital and the 2p orbital as the valence orbital. And here maximum 2 electrons and here 6 electrons can be accommodated. And you can see here 4 valence orbitals, 1, 2, 3 and 4. Whereas when you take the third period, it consists of 3s, 3p and 3d. So total 9 valence orbitals are there for the bonding. So of course the properties will vary from the other elements of the group. That is the one anomalous behavior. The second thing is, if we take this one into account, we can see the first member of each group is having a covalency of 4, because maximum the 4 valence orbitals are there, so covalency is 4. That is boron can form only BF4 minus complex or this type of complex, whereas the other member of the same group, they can expand their valence shell to accommodate more than 4 pairs of electrons, like aluminium, which is coming under the 13th group itself. AlF6 3 minus compounds can be formed. So with this we can understand the first element will be having the covalency 4 or the 4 valence orbitals are there. So of course they can form different type of element compared to the other elements of the group. The second or the next anomalous behavior is the diagonal relationship. We move diagonally across the periodic table. In the second and the third period, they show some similarities. And even though the similarity is not same as we see in a group, it is quite announced or pronounced in the following pair of elements that is to be noticed. That is like lithium, beryllium, boron and carbon is of the second period. Sodium, magnesium, aluminum, and silicon is the third period elements. But they have some similarity in, like diagonal means lithium and the magnesium. This is for which group? First group. This is for second group. And here the diagonal relationship is like this. Then for beryllium, aluminum, boron, silicon, they will be having some similar properties. Not as much as in the group how they are having the similar properties, but still they are having some properties. So this is said to be what? Diagonal relationship. So how we can give the definition? The similarity in properties existing between the diagonally placed elements is called diagonal relationship. So this is how we can define the diagonal relationship. And the similarity, as we said, for lithium and magnesium, it is similar. How we can say is lithium and magnesium both are hard in nature, both are soluble in alcohol, or how we can say the other elements, they are not soluble in alcohol, insoluble in alcohol. Then react gently with water. These two elements, they react gently with water. So these three qualities are similar for these two elements, lithium of first group, magnesium of second group, which are under the diagonal relationship. So this way we can explain the anomalous behavior of the second period elements. The next periodic trend is the chemical reactivity. The maximum chemical reactivity at the extreme left, that is among the alkali metals, is exhibited by the loss of electron. And if the loss of electron is there, it forms cation. And at the extreme right, that is among the halogens, they show gain of electron. That means there is the formation of anion. So this is the chemical reactivity at the right and the left of the periodic table. That is, they form the cation and anions when they lose or gain the electron. This property can be related with the reducing and oxidizing behavior of the elements. How this can be done is we have to learn the reduction and oxidation process, where we have to learn oxidation is loss of electron and reduction is gain of electron. So with this we can understand that where is the oxidizing nature and where is the reducing nature in the periodic table, which side among the alkali metals or among the halogens, we can understand. Thus, the metallic character of an element which is highest at the extremely left decreases, and the non-metallic character increases while moving from left to right across the period. If we consider the reaction of the elements with oxygen only, we'll take one example, that is, the elements on two extremes of a period easily combine with oxygen to form oxides. The normal oxide formed by the element on the extreme left, that is, the alkali metals, is the most basic. If we are giving the example, that can be Na2O, sodium oxide, whereas that formed by the element on the extreme right is most acidic, that is Cl2O7. Oxides of elements in the center are amphoteric, and one more type of oxide is there which are neutral. Now how we can define this thing is amphoteric oxides behave as acidic with bases and as basic with acids. They have the both quality, whereas neutral oxides have no acidic or basic properties. So this way we can explain the four types of oxides in the periodic table. With this we are concluding the chapter. Thank you.